So here's the final video in which we'll do a derivation for the rotational inertia of some particular shape when rotated about a given axis. We often say I is equal to the integral of r squared dm. An even simpler approach would be I equals the integral of di. Anyhow, let me show you some of the shapes we've already made derivations for. We started with this one. In fact, we found that this was a very easy derivation, nearly trivial. And then I think the next couple that we got into were the rod rotated about its center, 1/12 ml squared, a rod rotated about its end, 1/3 ml squared. From there, we moved on to a solid cylinder or disc rotated about an axis passing through its center. We said that's 1/2 mr squared. In our most recent video, we found that the rotational inertia for a spherical shell is 2/3 mr squared if it's rotated about an axis passing through its center. So for this video, we're going to derive the formula I equals 2/5 mr squared for the case of a solid sphere. Now, just to let you know, that's going to leave us with 1, 2, 3, 4 others that have not been derived. I would probably leave it up to you as a good exercise or practice to try to verify the formula for a slab rotated about an axis passing through its center. But this is the lesson for today, a solid sphere about an axis passing through its center. So in this case, we'll start with I equals the integral of di. Now, what do we mean by di? Well, think of it like this. We already found that for a spherical shell, I is equal to 2/3 mr squared. If I were to make a small spherical shell and then stack around that a larger spherical shell, and yet a larger spherical shell, and still larger spherical, you know where I'm going with this one. Again, this is like that Russian doll, the Matryoshka. If I nest together a bunch of hollow spheres, I can build up a solid sphere. So let's pick any one of these hollow spheres, and then I really can't say that I equals 2/3 mr squared because the mass of this hollow sphere is not capital M. We reserve capital M as the mass of the entire solid sphere. And we refer to r as the radius of the entire solid sphere. So we would probably say something like the mass of this spherical shell, which is part of the entire sphere, is a mass of dm, and it has a radius we'll probably just call lowercase r. And so I think we should say that the little bit of rotational inertia that contributes to the overall rotational inertia of the whole solid sphere, the little bit of rotational inertia from that spherical shell would be 2/3 times its little bit of mass times its particular radius squared. And so if I want to get the total rotational inertia for the whole gosh darn solid sphere, I'm going to have to add up the rotational inertia of that spherical shell plus that spherical shell plus, well, you see where I'm going with this one. I'm going to have to add up all the little bits of rotational inertia. That's what this statement's all about. And now we know what we can substitute for di, 2/3 dm lowercase r squared. So step number 2, I equals the integral of 2/3, how about r squared dm? And let's consider what we can substitute for dm. Uniform density is the name of the game one more time. This time we'll think of density in a traditional sense, kilograms per cubic meter. How do I determine the density of the entire solid sphere? That would be the total mass divided by the total volume, and the volume of a solid sphere is 4/3 pi r cubed. Well, I should get the exact same density in kilograms per cubic meter if I just take the fractional mass of one of my spherical shells divided by its fractional volume. dm is therefore m over v times dv. Okay, step 3, I equals 2/3 the integral of r squared times m over v dv. What's dv? What's dv? Well, if that's the inner wall of the spherical shell, and that's the distance to the outer wall, then I suppose the thickness of the spherical shell is something like dr. And there's an r number 1 and an r number 2. And as long as it's an infinitesimally small spherical shell, this dr approaches 0, yet is not exactly equal to 0. So the surface area of the inner surface would be 4 pi little r1 squared, and the outer surface would have a surface area of 4 pi little r number 2 squared. But r1 and r2, for all practical purposes, are equal when it's infinitesimally thin. And so all I have to do to get a volume is project that amount of surface area through a thickness of dr. So all I'm trying to say is dv is equal to 4 pi r squared dr, which gets us to step number 4. The rotational inertia should be 2/3 capital M over V times the integral of r squared times 4 pi r squared dr. I equals, let's see, 4 and 2 gives us 8/3. And then we've got a m and a pi, m, pi, and now in place of v, that represents the volume of the whole solid sphere. That's 4/3 pi capital R cubed. All right, and what are we left with? R squared and R squared gives us R to the 4th dr. This 3 cancels this 3. That pi cancels that pi. 8 over 4 is the same as 2. So we have in step 6, I equals 2m over r cubed, the integral of r to the 4th dr. Now limits of integration. Okay. Oh, the smallest spherical shell that helps build up the whole solid has a radius of 0, and the largest spherical shell that builds up the entire solid has a radius of capital R. So our limits of integration couldn't be simpler, from 0 to capital R. And this comes out to 1/5 capital R to the 5th. So if we put it all together, we finally get what we're after. I is equal to 2/5 m over r cubed times r to the 5th, and that cancels to give us an r squared, and we've got it. Indeed, I is 2/5 m r squared. Scroll back up, make sure we got it right. Indeed, I is 2/5 m r squared. Yay, physics.